video will cover the topic of ionization energy. Hopefully you will gain an understanding of its concepts as well as be able to apply these learned concepts to other trends in the periodic table for a better understanding. Ionization energy is defined as the amount of energy to remove an electron from an atom or molecule. By removing an electron, the atom or molecule becomes positively charged, which makes it a cation. Therefore, ionization energy can also be referred to as cationization energy. Some elements can have several ionization energies, referred to as first ionization energy, second ionization energy, and so on. The first ionization energy is the energy required to remove the outermost highest energy electron, and the second ionization energy is the energy required to remove any subsequent high energy electron from the cation. Each succeeding ionization energy is larger than the previous due to the increase in ZF, which is the net positive charge attracting an electron in an atom. The influence of the ZF value on atomic trends will also be a concept further explored throughout this presentation. So just as a little background history before we dive into the deeper concepts, in 1869, a Russian chemist known as Dmitry Mendeleev discovered not only ionization energy but also created periodic law and created a loose version of the periodic table that he called the periodic system. Most quantitative and qualitative characteristics can be described by Coulomb's law. I've included a picture of the equation of Coulomb's law in the presentation. So Coulomb's law describes the relation of electrical force between two charges and the quantity of charge on the objects. According to Coulomb's law, we expect electrons closer to the nucleus to have a lower potential energy, which require more energy to remove from the electron. Non-valence electron clouds act as electron shields, which reduce the nuclear charge felt by valence electrons. So before exploring ionization energy, it's helpful to begin with understanding how the atomic radius trend works across the periodic table. As you can see from the picture, the atomic radius decreases from left to right. This is because as the atomic number increases, both the protons and electrons increase by the same number. The electrons are added to the valence shell, and the protons contribute to a greater nuclear charge in the nucleus, also known as the ZF. Going across a period, the distance and electron shielding remain constant. However, the increasing net positive charge strengthens the attractive charge, which pulls the electrons closer to the nucleus in an atom. Thus, the result is a smaller, denser atom in size. Ionization energy can also be understood to correspond to atomic radius. As electrons are brought closer to the nucleus across a period, more energy is required to remove them. When looking at a periodic table that reflects the trends of ionization energy, we can observe that the directionality of increasing ionization energy is opposite to the trend of increasing atomic radius. Going back to the original definition of ionization energy, it is the amount of energy required to remove an electron from an atom. From learning about the characteristics of atomic radius, we can relate that because the ZF increases across a period, the amount of ionization energy will also increase across a period. The smaller an atom is, the more difficult it will be to remove an electron from the valence shell, because the electrons will be closer to the attractive positive nucleus. Here is an example of an ionization energy versus atomic number graph. Each maximum of the graph with a labeled element represents a noble gas, the last group found on the periodic table. After each noble gas, a new period starts. So when we look at helium, lithium comes after, then beryllium, boron, carbon, nitrogen, oxygen, fluorine, and then the other noble gas. After argon, the distance between the noble gases increase. This is because of the elements on the periodic table increasing in the period of group 4 and after. We learned before that the general trend of ionization energy increases from the bottom left to the top right. However, there are exceptions that do not follow the expectation to increase as observed on the graph between each noble gas. Interpreting the part of the graph that is between helium and neon, we can see that both boron and oxygen decrease in ionization energy after the preceding element. We will further explore why this occurs. Atoms are always trying to be stable. Atoms are most stable when their valence shell is half filled or full. To understand the reason behind the exceptions to the periodic ionization energy trend, it is important to understand the relationship between energy and stability. Stability defined is a low state of energy. For example, we think of a ball at the top of a slide being less stable than a ball that is at the bottom of a slide. If it is at the bottom of the slide, it will just sit there, with no chances of it rolling anywhere, assuming it's on level ground. If it's at the top of a slide, it could roll down. This example illustrates the different levels of energy and its potential. In the same understanding, when an atom is stable, it has a lower energy than an unstable atom. If a stable atom becomes unstable, it must absorb the energy from somewhere else. If an unstable atom becomes stable, it must release that energy. So we know that nitrogen precedes oxygen on the periodic table. We also know that the ionization energy trend increases from left to right. So we would expect oxygen to have a higher ionization energy than nitrogen. But we know this is untrue because we just found out that oxygen is one of the exceptions on the periodic trend. So we're going to investigate, why does oxygen have a lower ionization energy than nitrogen? The first thing that we'll do is write out the electron configuration for nitrogen before losing an electron. After removing an electron, we notice that it has moved from its stable state to a half-filled shell to an unstable state. So it's moving from a 2p3 to a 2p2. And then we remember, when a stable atom loses an electron to become unstable, it releases energy. So it would increase the amount of ionization energy that is recorded. The next thing that we can do to compare is draw the electron configuration for oxygen. After the ground state configuration is drawn, we can also draw the electron configuration after an electron is removed. So, after the configuration is removed, we see that it has moved from a 2p4 orbital to a 2p3. So, an unstable atom has now become stable. And we remember previously covered that when this happens, energy is absorbed. So, in the process of removing an electron from the pull of the nucleus costs energy. Even though this happens, we get a small of energy back, which makes up for the difference in ionization energy between nitrogen and oxygen. which is why oxygen has a lower ionization energy than nitrogen. To our understanding of ionization energy and its explanation through electron configurations, we can use what we now know to explain an exception that we saw in ionization energy, and is also an exception in the trend of atomic radius. Nitrogen has a smaller atomic radius than oxygen, for which it precedes. We recall nitrogen having a 2p3 arrangement in the electron configuration that we drew in the example just before. The 2p orbital is half-filled, therefore being stable with a lower energy level. Recalling the electron configuration for oxygen, there was a 2p4 arrangement. One of the three 2p orbitals has a pair of electrons, which leads to a greater repulsion between electrons, and therefore increasing the atomic radii slightly. I hope this tutorial has given you a greater understanding of ionization and how it works, Coulomb's law, and electron configuration, all of which can be applied to understanding all of the other periodic trends when examined.